And again, I'd like to welcome you today to our webcast introducing Amazon Redshift with Ben Butler, who is our presenter today. Ben, I'll hand it off to you.
Thank you, Aurora. Hello, everyone. My name is Ben Butler, and I'm a worldwide public sector solutions architect. And if you have further questions later on after the webinar, you can contact me at butlerb@amazon.com. And we appreciate your time and interest in learning about Redshift today. We will introduce Redshift and talk about why we built it, how we achieved the performance that we're going to talk about, and its ease of use. We'll start with a brief overview of Amazon Web Services and database services in particular. We'll then look at the reasons we created Redshift and describe the services. So this is a high-level overview of the portfolio of web services that we offer built on top of our global infrastructure. The compute, storage, and data services are the core of our offering. We then surround these services with a range of supporting components like management tools, network services, and application augmentation services. All of this is hosted with our global data center footprint, which encompasses 9 independently operated clouds, which we call AWS regions, that allows you to consume services without having to build out facilities or equipment. There's a lot of equipment powering our web services, and in fact, every day, AWS adds enough server capacity to power Amazon.com in 2003 when it was a $5 billion enterprise. And so let's do a quick review of our managed database services. We're just going to focus on these, and then we'll go into Redshift. Database services is a foundational service of AWS. Database service customers are offered a broad choice for their database platforms, enabling them to deploy the best data store for their use case. All database services are fully managed, which means they provide automated management of low-level administrative functions. This enables developers and administrators to focus on application functionality and performance rather than on patching and backup maintenance. RDS is a fully managed SQL database service for OLTP workloads, and it runs with 3 database engines, MySQL, Oracle, and SQL Server, in a high-performance, durable configuration that can be provisioned in minutes, and in a multi-availability zone, or known as multi-AZ replication, is a feature of this service. Designed for production instances, multi-AZ provides a one-click disaster recovery to a remote data center or availability zone for fast failover and maximum data protection. Elasticache is a fully managed Memcached compliant in-memory caching service that allows you to offload read queries for in-memory clustered with EC2 instances. And then we have DynamoDB, which is a fully managed NoSQL service running on solid-state hard drives for massively scalable, high-throughput, low-latency workloads. And then we'll talk about Redshift, which is a fully managed, fast and powerful, petabyte-scale database warehouse service, which will be the focus for today's webinar. And it's a warehouse that's been specifically enhanced for the cloud and was developed after many customers requested a fully managed, high-scale option for analytical workloads. So for anyone who's had experience with traditional data warehouse services knows that it's really expensive and really complicated to manage. You see that on that piece of paper there, how many things you have to go and figure out what to pay for. You have to get the licenses, you might have to have multiple licenses, you need the number of cores you need and multiply it. It gets expensive pretty quickly. And yes, as Gartner reported, points out that enterprises average 3 to 4 DBAs per data warehouse that they have to hire for each data warehouse that you have. So it's really expensive and really complex for tuning and administration. So customers have told us for years that they're unhappy with these types of solutions. First of all, large companies feel that they're paying too much and that these data warehouses are difficult to manage and too hard to scale. And for smaller companies, although it has never been easier than today or less expensive to collect and analyze data because of the cloud, they can't afford these expensive data warehouse solutions to store this data long term, and they end up having to throw out a lot of data. So customers have asked us to look into this space, and we thought to ourselves, what would it take to do data warehousing the Amazon Web Services way? It would have to be easy to get started, self-service, be able to scale up massively. We wouldn't want anyone to pay up front and have a pay-as-you-go model. This cost model is also almost as important as having a low price. And on-demand, utility-style pricing is always a popular request. And it has to have really fast performance at a really low price and easy to use. So these requirements were generally in response to price performance of the value that customers wanted and felt were not getting from other options. So we had this service that we need to be able to have it open and flexible and work with popular business intelligence tools that people are using, because there's a data warehouse ecosystem already in place that's healthy with a lot of technology vendors, and especially those who focus on data movement and business intelligence. And so we wanted to create a data warehouse in the same style as our RDS service and be able to provide an open framework through SQL, ODBC, and JDBC connections to be able to build out Redshift. So introducing our Amazon Redshift, it's doing data warehousing the Amazon way. It's easily and rapidly available to analyze petabyte scales of data at 1/10 the cost of traditional data warehouses, and automated deployment and administration, and compatible with popular business tools. Redshift refers to the astronomical phenomenon which was used by Edwin Hubble to determine the universe was expanding. Amazon Redshift is a fast and easy to use, fully managed petabyte scale data warehouse service in the AWS cloud, and is designed to help customers to make sense of an ever-expanding universe of data and to function as a central component in a big data strategy. So most data never makes it to the warehouse, and there's this large data analysis gap. Enterprise data is growing over 50% yearly as applications can automate data, and also with the advent of cloud computing, be able to create and analyze data is growing at an exponential rate, much more so than the speed or the size of data warehousing. It's only growing at a 10% yearly clip, and so most data is left on the floor. So various analysts have attempted to quantify this gap generated by the applications and data that makes it way into the analytical environment. The general trend is that this gap is large and growing, and people just can't capture and process this volume of data that they're generating. So we're specifically designing Redshift to eliminate two of those major barriers to broad adoptions of analytics: effort and cost. Operational data, because it doesn't find its way off to the floor, it's not being used, and we're trying to flip that script and be able to have Redshift enable that. So we set out to build this fast, powerful, petabyte scale data warehouse that's a lot faster. Our goal is 10 times faster, a lot cheaper, 10 times cheaper, really easy to use, and it is our fastest growing AWS service. It was conceived with the core set of objectives of being the faster, cheaper, and easier to use than any other data warehouse alternative. To achieve these goals, every aspect of the service has been optimized for data warehouse workloads. With extensive use of automation, I/O efficiency is especially important for performance, and eliminating unnecessary I/O has been an area of great focus for the Redshift team. The goal is to reduce this undifferentiated heavy lifting. So in a data warehouse, we want the customers to increase the differentiated effort by focusing on the uniqueness of their application rather than spending time on backups, on trying to scale, patch, work on the operating system, or other hardware administration. We want to leave that muck to Amazon to work with Redshift. So Amazon joining the fray here with data warehousing, how are we increasing performance that's not already done before? And we're focusing really on I/O. So in Moore's law, memory capacity and CPU performance double about every 2 years. But there is a lag with hard disks, and they have mechanical constraints. And so performance doubles only about every 10 years. So because of that, the input-output operations to disk, they dominate data warehouse performance today in terms of bottlenecks. So we attack this in several different ways in which we'll go through about how do we dramatically reduce this I/O. First of all, a significant factor is Redshift high performance is in the use of columnar storage, which is optimized for scan operations. I/O becomes one of those important factors and bottlenecks, and columnar technology helps reducing I/O need and only concentrate on the I/O that is considered that you need for your queries instead of scanning every single item. Some queries, when you scan, you throw away 3/4 of the data that you're able to scan because you only need some section of it for your actual query. And so also what we do in the columnar storage is that we're able to do data compression. And being able to do data compression, we augment how each of those fields are put into Redshift, and we look at the data and analyze it, and then determine the most optimal compression mechanism to be able to place on those rows. And by doing that, we can get typical data workloads to be 2 to 4 times smaller than a traditional relational database. And indexes are not required in Redshift because the columnar storage is already physically optimized for scan operations. This relative savings can be even greater, sometimes 4 to 8 times in data compression. So a 4 terabyte traditional data warehouse service storage can be 1 terabyte in Redshift. So you get these compression benefits and similar data of all these columns that are stored together, and take advantage and to use this compression and use different types of compression to enable efficiencies. And then we use zone maps. So zone maps allow you to keep track of, allows us to keep track of the minimum and maximum value of each block that's stored on disk for the columns. And so when you run queries, you can skip over these blocks that don't contain the data needed for a given query. So when I mentioned earlier where instead of having to scan the whole database to get all the result sets and then filter off of it, we can skip entire blocks that don't matter for that particular query. And so that enables us to minimize unnecessary I/O. And furthermore, we also use direct attached storage and large block sizes. So this direct attached storage, and I'll get into how it's architected with the types of storage that we offer and the size, but it's directly attached to the Redshift servers, so not using the network for local storage, instead using local storage and using large block sizes of 1 megabyte. And so we have high performance I/O drives, and the CPU and memory are all local on each of the compute nodes. And we take care of all the local management of resources. And so when we do a read for a scan, we get as much relevant data as possible with large block sizes. And this enables us to get the most performance out of the system. And then lastly, Amazon manages the durability of the data that's being stored on these local drives for you. So let's take a look at the Amazon Redshift architecture. So you would connect to the cluster using a JDBC or ODBC client driver connection to a leader node. So this leader node is the SQL endpoint, and it's the only endpoint into the Redshift cluster. This leader node stores metadata. It coordinates the queries execution. What it also does is that it distributes jobs to the compute nodes that are running. So you can have one or more compute nodes, and then the leader node distributes tasks to those compute nodes. And so the compute nodes, they have local columnar storage, and they execute all the queries in parallel. And I'll get into a little bit about Amazon Redshift architecture and doing the massive load parallel programming architecture. And this allows you each of the compute nodes to work on these instances independently and in parallel, and then you can load this data from Amazon S3, our simple storage service, or also be able to load this for DynamoDB using a copy table command. And then there's also a single node version for our smallest extra large instance type, where you can use this where the leader node and the compute node are co-located, and enables you the ability to test the service out and to get started, but then you can scale. And we'll talk about being able to scale from the 2 terabytes to the 1.6 petabytes. So Amazon Redshift runs on optimized hardware. And so this server infrastructure was custom built and was made into a new EC2 instance type. And this instance type has been made available as a EC2 instance called HS1 8 extra large, which has 128 gigs of RAM, 16 cores, 24 spindles, and with the Redshift, you get 16 terabytes of compressed user storage. And then again, if that's a factor of 4, you could actually have potentially a 64 terabyte storage on that node and compress into 16 terabytes. And then you also get a 2 gigabyte scan rate. So we've taken this instance type, and then we've also taken 1/8 of it. And so we call that the HS1 8 extra large, which has 16 gigs of RAM, 2 cores, the 3 spindles, and 2 terabytes of compressed customer storage. And so this smaller instance type, HS1 extra large, is exactly 1/8 the size of the 8 extra large in all the dimensions, and so it's linear, as well as the pricing. So the extra large is 1/8 the cost of the 8 extra large. And then you can start small and grow big and grow either 2 terabytes or 16 terabytes at a time. But it is, when I talk about the clusters have to be homogeneous, meaning that the cluster has to have all of the extra larges or all of the 8 extra larges, but you can switch between the two. And we'll go through that when we talk about resizing. Okay. And so Redshift parallelizes and distributes everything. It's a clustered system, and it's using a massively parallel programming system. The leader node is your endpoint to interact with the Redshift cluster. You can't remotely log into it like SSH, but what you do is you have a SQL endpoint that you connect to with either a JDBC or an ODBC driver. And so this leader node then turns your SQL statements, so you submit SQL statements to the leader node, and it turns those into an explain plan for the optimizer, and the optimizer generates a query plan that uses statistics stored in the system tables on how the data is physically laid out on all the compute nodes, and then the execution engine turns that plan into compiled C++ code, and then that code gets distributed to each of those compute nodes in parallel. So there is a small penalty while that compilation is in progress, but what happens is when you have subsequent queries of that same type, and you're just changing the parameters, all those compiled code is already distributed throughout the system. So running that query again, you won't get that same impact as you would if you query it the first time. And so there's also multiple threads on each of the compute nodes in terms of slices. And this enables us to divide and conquer the workloads. So this is a scale-out architecture, and you can add more compute nodes up to our limit of 100 for the large ones and 32 for the small ones. And so not only do you get more storage by adding more nodes, but you're also getting more compute and more memory for that cluster. We also focus on load. So we want to make loads parallel as well. So we don't add time loading a cluster. If you have 2 nodes or if you have 20 nodes, since they're all working at the same time, data can be loaded in the same time frame, and also can be loaded by a single copy command, either from an S3 bucket or a DynamoDB table. You can use SQL insert statements as well, but those are not done in parallel. They're actually done through the leader node. So depending on your data requirements and your velocity of load, you would want to consider using the copy command instead as a best practice. And so when you load this to each compute node, it's done in parallel. And then each compute node has a process called a slice, which we talked about. And so the extra large has 2 slices, and the 8 extra large has 16. So when you're doing a load, you should map the number of data files loading to your cluster to the number of available slices in your cluster, so that each slice, so each computing process, is taking a piece of the data and loading it in parallel. And then all of the nodes are connected by 10 gigabit Ethernet fiber, or Ethernet network. And so if the data needs to be redistributed between the nodes, it will happen automatically and expeditiously. And one part of the columnar system is that whenever you need data that needs to be joined, another best practice is you want to store the data on the same node that you're joining so that the joins are node local, and they'll perform better than having joins that distribute across the network amongst multiple compute nodes. And so because of that, one of the options that you have when you create tables is your choice of a distribution key. This is how you physically lay out the data. So for example, if you have a customer ID for an account and the customer sees ads and then the customer also has accounts and transitions and transactions, you may want to distribute your data by that customer ID. So if you have to do joins on ads and transactions, then all of those joins is node local, and you'll get better performance in terms of reduced query times. And all of this is done behind the scenes. So what you do is you pick the number of nodes, define your tables and your distribution and sort keys, and then load your data. And as I said before, you can load it with the SQL insert command, but it's better to do it through the copy command. So there's a data processing pipeline where you format the data to put it either into Dynamo or S3, and then do the massively parallel copy into Redshift. We also invested a lot of time in a continuous backup and easy restore process. Backups are done at the node level. They're done in parallel, are automatic, and incremental. So anytime data changes in the cluster, we'll kick off a backup process to asynchronously copy data to S3. So not only are we using S3 as a loading point, we're also using it as a way to back up the whole cluster. And so we only copy that data to S3 for data that's changed. So if nothing's changed in your cluster, you won't see any additional snapshots in S3, only when you do incremental. And so there's also a system snapshot period, and that's configurable. The default is 1 day, but you can set it up to be up to 35 days. And then we'll just age out the data as that time window slides past your time. And so you can also create user snapshots at any time. So a snapshot basically gives you a block-for-block copy of your entire cluster, and so you can freeze that cluster state and enables you to create an exact copy of it. And so you can trigger that snapshot manually, either with the console or API call, or you can automate it using a script that does that. And that frozen cluster state will be retained until you explicitly delete it. So if you ever delete a cluster, you'll also get an option to do a final snapshot of it. So when you delete the cluster, you release all the compute nodes and the leader nodes of that cluster, so you're not incurring charges. But if you want to reload that cluster to have the exact same state before you released it or terminated it, then that's why you'll want to use those manual or final snapshots. Another feature that we offer is that we have large instance types with 16 terabytes of storage. And so if you're restoring from a cluster, you don't want to have to wait for all the 16 terabytes to load before you can start doing your queries. So we spend a lot of time in optimizing and doing a streaming and restore, which is also coming from S3. So what we do is, as you're making requests, we're paging data from S3 to the data that's needed, and this is also all done automatic and behind the scenes as part of this managed service. And so what we've seen, depending on time-related data that for querying, once you start getting 3 to 5% of that data streaming and restored from S3, for most of our customer workloads, that's starting to work using the streaming restore and not having to wait for the full node of each of the compute nodes to load up with data. And now we'll also talk about Resize. So Redshift makes scaling up and scaling down very easy. The Resize experience in Redshift has been very popular with anyone who's been through a scale-up exercise with the traditional data warehouse technology. Planning and preparation using traditional technology often takes weeks, and when it's time to execute, that effort is equivalent to a full data store migration. But behind the scenes of what we're doing with Redshift, what we do is we place what we call, say, the original cluster in a read-only mode. And then what we do in parallel is operate a new cluster, a newly requested cluster to the target size. And so it's important to note when you want to downsize your cluster, you want to make sure your new target cluster is large enough to hold with the size of your original cluster. So you may have several nodes at 64 terabytes and you want to go down to 32 terabytes. You just want to make sure your original cluster is less than 32 terabytes in size to be able to scale down. But the data is, again, copied in parallel from one compute node to the other compute node, from the current cluster to the new one. And that rate of transfer is limited by the smaller of the two clusters. So that depends if you're upsizing or downsizing your cluster. And so clients continue to communicate with the leader node of the original cluster while the new cluster is being built out and then moving the data over. And so the leader node of the original cluster is available for read queries, but the writes are suspended during this resize process. And so we're pausing the writes, we're creating that new cluster, we're copying everything over to the new cluster, and when that process is finished, we then do a DNS switch, and your applications don't have to change, and you're able to move from your old cluster to your new cluster seamlessly. And by the way, you don't pay for the new cluster until that DNS switch has happened. And then we decommission the source cluster and get that out of the way. And this is also a simple operation via the AWS console or using the API. So this enables you to resize and scale up and scale down your cluster with the only requirement making sure that the new cluster can contain the new data. So talking about scalability, so from a scalability perspective, we worked hard to make it easy to scale up as your needs required. We talked about the resize. You can start with that single extra large node. All right? It has 2 terabytes of compressed storage on it. And then you can cluster a maximum of 32 of these extra large nodes at a time. And so that gives you 64 terabytes of total storage if you do all 32. And again, you get, with the smaller node size, you get the option of having basically a single node cluster where the leader node and the compute node are co-located on that instance type. But then, should you want to scale up, you can scale up to the 8 extra large instance type, which then gives you 16 terabytes for that node. And then you can network 100 of these. And so with this, the smallest cluster you can have is 2. So that gives you the smallest size of a 32 terabyte cluster using the 8 extra large. And you can have 100 of those, which gives you a 1.6 petabytes, and this is the petabyte scale of storage. Now, we've already received requests from our current customers that are using Redshift to increase this limit. And so we're looking into that at this time. We're trying to take those requirements in and see what we can do to make it larger. But it's also important to note, from a price perspective or a performance perspective, there's no difference of running the 8 extra larges to 1 extra large. It really comes down what you want your scaling increment and your total size of your cluster to be. Because the 8 extra large is exactly 1/8 of the large, is 1/8 of the extra large instance, and exactly 1/8 of the cost. So we're also making it easier to determine what your cluster will cost you. And then again, each of these clusters that you create have to be homogeneous of the instance type. So you can have a cluster of 8 extra larges and extra larges, but not a mix of the two. And so talking about price, we're priced to let you analyze all of your data. So we built Redshift to focus on the performance and the price and the ease of use. And we want to make it easy and cost-effective for our customers to analyze their data and eliminate the need in having to throw your data away because it was too expensive for the data warehouse. And so pricing starts on our extra large instance with 2 terabytes of storage at less than $1 an hour, so 85 cents to get started for the on-demand rate. And then so if, I don't have it in the chart, but the 8 extra large is exactly 8 times of that, so $6.80 per hour. We also have reservation models. So if you're familiar with EC2, not only is it pay-as-you-go, but the more you use and the more you know you're going to use, the more you can save. And so how that works is you can prepay some upfront fees and get a lower hourly rate. Because reservations give AWS insight into capacity needs, and so by reducing this uncertainty of the capacity needs, it reduces our costs, which we provide back those cost savings to our customers in the form of reduced hourly rates for the reservation model. And so we have two types. You can reserve instances for 1 or 3 years. And so you can see it's a little over $3,700 to do on-demand per terabyte. So if you have that 2 terabytes, that's the price per terabyte. But then you save 40% if you do a 1-year reservation because the hourly rate goes from 85 cents to 50 cents. And so you have a lower effective hourly price, which is basically taking the upfront payment, adding up the new price per hour times the number of hours to get the $21.90, which is about the 40% price reduction. And so if you do the 3-year instead of a 1-year, then you can get it down to under 23 cents an hour to run your petabyte scale cluster at a per terabyte cost. And so that gets you down to under $1,000 per terabyte per year. And if you look at the cost of typical data warehouses, costs can run between $19,000 and $25,000 per terabyte per year. So this is a significant change in the pricing in terms of cost, but also in the pricing model of this utility model of pay-as-you-go computing. So this pricing model has already achieved 2 main benefits for our customers. 1, a dramatic reduction in costs, and 2, customers are now using data warehouses for more use cases than before, and we'll go over some of the popular use cases later on in the presentation. And so there's no charge for the leader node. That's also another benefit. So that's another compute instance we have that it's just built into the hourly rate of your cluster. And so if you want to calculate the cost of your cluster, you just calculate the hourly rate times the number of nodes. It's as simple as that. There is no data transfer in and out of Redshift as a cost, although standards S3 and VPC transfer rates apply. So you can look on our website for those pricing. But it's no different than what you would do for normal S3. So having to spend time installing hardware and software, doing patching, backups and scaling and tuning prevents our customers from focusing on their application, their data, and the insights and decisions that they could drive from being able to analyze that data. So we want to reduce that time of installing the hardware and software and focus it more on the customer's benefit. And so because of that, we designed the Redshift to be fast and easy to provision. It takes about 15 minutes to provision, and I'm going to do a quick little demo and showing how that's done just to launch a nominal Redshift cluster. And then that's much faster, right? What I'm going to show you on screen is much faster than waiting weeks to provision traditional data warehouse clusters. Okay, and then we can monitor query performance. And then you can spend a lot of time developing the metrics and focusing on those. And then we handle the disk failures, the performance, and the durability as part of the managed service that's built into the hourly rate. We're doing the backup to S3 that's continuous and incremental and automatic. And we have these APIs and command line tools to control this so you can get this as a fully programmable data warehouse from your perspective. So provisioning a data warehouse in minutes. And so there's 4 quick steps. I'll do a quick launch in just a second. I'll share my screen. But we have you put in the cluster details, the node configuration, the additional configuration, review it, and then launch the cluster. And then it's pretty much point and click. And then again, with the single extra large, you can have 1 node. And then we also fully support VPC in Identity and Access Management, IAM, so you can control who is allowed to describe or create your clusters. So hopefully you can see my screen. They'll let me know if you can't. I'm on my console right now in my account, and I'm going to the Redshift Management Console. I've already launched a couple clusters, which we'll connect to in a little bit, but I just want to go through the process of launching one and showing you how really easy it is. So So you launch the cluster, you give a cluster identifier, I'll just call it demo cluster, and then I'll call it and give it a database name. So this is the first database. You can add multiple databases at a later time, but during the initial console, you just give it a database name. Then the database port is 5439, but you can also change that. And then you put a username. And a password. Hopefully I got that right. Oops. Let me just do a simple one here to get close. And put in a password. And then here you can pick the node types. And so you have the HS extra large, HS1 extra large, and the 8 extra large. I'll just pick an 8 extra large. And then that defaults to a multi-node environment. If you do the HS1, then you can have that choice of a single node. So I'll do a multi-node. I'll leave it as an extra large actually, and I'll just pick 2 nodes. So you have to start out with 2, maximum of 16 here. You can increase this. There's a limit request. You can do 16 here, and then when you do the 100, you can also increase the limit there. And so we'll hit continue. We'll just leave these by default. You can also launch it in a VPC. You've got to create a cluster subnet group, and that's in the documentation how to set that up. It's pretty easy. And then you pick a security group, just like in EC2, of where that's being available. You can also say which of the availability zones in your region that you want to deploy in. I'll leave it no preference for now and hit continue. And then you review. And so you're going to start accruing charges. It's giving you some examples here of your database configuration, your configuration information, your security access, and then you hit launch cluster. And then you can view your cluster in your dashboard, and it's in a creating status. And this takes about 15 minutes to provision and then start loading data. And so I already have a couple there. I will show a connection of that in a little bit, but I just want to, we'll get back to the presentation. So after you provision it, you start connecting to it and running queries against it. You can monitor query performance, which is a common use of your clusters to look at the performance. And we spend a lot of effort in developing our console to provide you the information on your queries, and so to help our customers get a sense of what resources are being consumed. In this example, this is a time chart. The horizontal bars are the queries that have run on the cluster. If you hover over them, it shades the resource that you can see in that light blue. What are the resources that have been utilized when that query has been executed? And so that pink is the leader node, and you see that the CPU utilization is very low because it's just doing the coordinating, and that's pretty good. You'd be concerned if that was pegged high. And then when it's running the queries, so you can see over time, we're running a lot of queries over a short period of time, and so you see those 2 spikes of a 2-node cluster of Compute 1 and Compute 2. You see that they're launching up nearly in parallel. So that's giving you a good indication that it's distributed pretty evenly. If you were only seeing one line spike up, that may be because of a co-located join, or that your data is distributed not in a non-even fashion. So it gives you an insight as to what you need to do. If you click on the right, there's a SQL statement. So it shows you, when you click the queries, it shows you the SQL commands that you operated for each of those queries as a SQL statement, and then how the leader node has converted that into an explain plan that goes in detail of how it's creating the steps to run that query. And so you can look at those and then also see the metrics as well. And then the point-and-click resize. And so this is very easy as well, and I'll just go ahead and do that. I'm going to go back to my console. I'll hit share my screen. I've got this example cluster. It has only got 1 node, and I'm just going to click resize. I will say multi-node, and we'll click 3 nodes and hit resize. Oh, I hit my quota, so I've got that soft limit as well. Let's see if I can just see if I can set this to maybe 2. Okay, I'm able to set that to 2. I'm hitting mine because I'm running multiple clusters in different accounts. Okay, so let's go back. I'll go back to my presentation here. And so point and click resize is very easy. And it allows you to increase resources. So instead of having to do that full-scale data migration effort, it's more of a point and click or a command line tool to be able to do that. And again, like I said, when you do the resize, it distributes that cluster in a new cluster. While that's being done, you do the reads, the writes are suspended, and then it fails over. So we also have built-in security, and we took advantage of the security features that Amazon already offers when we launched Redshift. So we have SSL to secure the data that's in transit. You'll be able to enable this on the client side and connect to make sure all data flows are encrypted. So you use SSL to have encrypted data connection between Redshift, S3, and DynamoDB as well. And so SSL can enable you on your end, and you can choose that at any time that you want. And then as for data encryption at rest, should you choose it, it's hardware accelerated AES 256-bit encryption. We do this at a very low level in the subsystem so that every block that's ever written to disk or loaded or with temporary data or just loaded data, everything is encrypted at rest. And we are doing continuous backup, right, as part of the backup. And so at the block level, every block that's backed up to S3 is also encrypted. And then we also use a multi-layer key mechanism where each block has a unique key to encrypt each block individually. Then there's a cluster key that encrypts those block keys. And then there's yet another key to encrypt the cluster key, and that's kept off cluster. And so we keep innovating in that space and look forward to that, but we have a very strong multi-layer key mechanism. And so that option to encrypt is done at creation time or resize time, and there is a 10 to 15% performance impact by our testing. And so we don't enable that by default. We let our customers make that decision. So each Redshift instance is also provisioned solely for the customer that created it. And each of those compute nodes are created in an internal VPC. And so a VPC is Amazon's virtual private cloud, and it's a way to logically isolate a section of the AWS cloud and set up your own network space and access your cloud resources privately. And so nothing can access these compute nodes directly. You can only interface the cluster through the leader node. And even the data node, the compute nodes, when you put data in them, it's a pull request from the compute node. Nothing's ever pushed onto those compute nodes. They're pulled from S3 or Dynamo or from the leader nodes during a SQL insert statement. And then you can also set up your own VPC doing your cluster subnet and then control access however you like for access to that cluster. Okay. And so another part of the operation is to take care of your data. We use local attached storage. It's ephemeral, and we use it for cluster performance. But as with EC2, when you have multiple terabytes on data on disk, having only ephemeral storage is not a good thing in terms of durability. So Redshift takes care of that durability management of your data. It's a theme of all of our AWS managed resources. So anytime you load data on the cluster, we'll synchronously replicate on multiple compute nodes within that cluster. So if you go to EC2 and you look at the 8 extra large, you actually get 48 terabytes of storage because it's 2 times 24 terabyte spindles. But you only receive 16 terabytes in Redshift because we're using the other 2 terabytes for redundant copies. And we're doing that all across the availability zones within a region when you do a snapshot, and we do a backup of that cluster. And so S3 is designed for 11.9 durability. It has a lot of scale to it, and it enables us to automatically and continuously and incrementally store that. And so we're continuously monitoring and automating the recovery of any node failures, pulling it from S3 or from the other compute nodes as we see fit. We reboot nodes. and that's transparent to the SQL clients. And so that brings us to integrating with multiple data sources. So we really designed Redshift to be the central data warehouse and central database repository, or this hub, with all of the different EC2 services. So we see customers who use traditional OLTP databases, either with RDS or running their own databases on EC2 or on-premise. And we have customers running NoSQL data stores on EC2 or DynamoDB, especially for real-time data capture, or using EMR. So using MapReduce or Elastic MapReduce, our Hadoop offering on EC2, to take unstructured data, put it into structured columnar format, put it in parallel to S3, which then we can import into Redshift. So Redshift is at this hub of being able to collect data for longer life cycles than previously been able to do before. And so we provide a lot of loading options, upload to S3, do an import-export where you ship hard drives to us, do Direct Connect, which is a 1 gig or 10 gig private fiber pipe to the cloud. And you can do those in increments, so you can truncate those and be able to do even larger scales. And then you can work with partners, data integration or system integrators that you see here on the slide that have optimized and being able to move lots of data into the cloud and being able to import it into Redshift. And so Redshift works with your existing analyst tools. So with the JDBC, ODBC connectivity, using Postgres drivers. So it's not a Postgres database engine, it's our own proprietary engine, but we use the protocol, the wire protocol from Postgres in order to interact with it. And then we have a lot of business intelligence tools that if they can use ODBC and JDBC connections and use SQL to make requests into databases, then they should be able to work with Redshift. And so we've had a lot of partners certify their own applications, and they've done so also on our marketplace to be able to connect to Redshift. And so we have a marketplace of, it's basically an app store of different services that can run on our cloud. And we also have a certain section for Redshift, so you can see some of the BI tools, such as JasperSoft, MicroStrategy, and Intunity, that have platforms that enable you to discover Redshift clusters in your account and be able to set up the connections to them. So we've had several customers. We're working on creating a lot of public case studies, but Kia, as well as Airbnb, they've done presentations where they've shown how they found benefits in Redshift. But I will talk about what we've done with Amazon. So our retail Amazon.com business is pretty big business, and it has a pretty big old guard traditional data warehouse solution. And we've been working with their database team internally for several months with testing and using of Amazon Redshift. And so their data warehouse, which costs several millions of dollars per year to run, has 32 nodes, 4.2 terabytes of RAM, and 1.6 petabytes of disk. And so again, this is costing millions of dollars to run. And so what we did was we took 2 billion records and 6 of the most complex queries that they usually run on this data warehouse and did a benchmarking on those. And we did it on a Redshift cluster of 2 16 terabyte nodes, the 8 extra large, and roughly around $32,000 per year to run that with reserved instances. And we got at least 12 to 150 times performance in being able to do that. And so the DBA team of Amazon.com said that they could probably tweak their database cluster to kind of match those Redshift improvements, but they would have to take a couple months to do so. Again, going back to the performance and tuning, undifferentiated heavy lifting that you would have to do to get this kind of performance, which you can get by the hour. And so I'm just going to quickly go through these use cases just because I'd like to show you a little bit about connecting to the Redshift cluster. And so we've got this reporting warehouse use case where you have a database that's, or ERP system pumping data into a relational database, which then you can offlift into a Redshift cluster. And then, again, that's the endpoint of being able to do reporting and BI. So you can use RDBMS for the online transactional processing, but then use Redshift for the online analytical processing for your reporting and BI tools. And then on-premises integration, because of VPC and also using our data integration partners, you can create secure tunnels into the Amazon cloud and also be able to use Redshift as if it was a private resource. And then there's live archiving for structured big data. So DynamoDB is a massively scale-out, unlimited size, provisioned throughputs of reads and writes of, if you wanted to, hundreds of thousands of reads and writes requests per second if you wanted to. And so you can use DynamoDB as this structured document NoSQL store, which then you can then provide as a source to import into Redshift. And then again, you can use Redshift as that hub to collect all that data. So you can use DynamoDB to handle hot data that's coming in very fast, and then using Redshift to analyze that offline, so to speak. And then you can use entity and transaction loading for big data using EMR. Again, you can have EMR process unstructured data that's being stored in S3, formatting that to fit into the profile that you need for Redshift, which is basically any byte delimited type of file, text file in UTF-8 format. And so you can have EMR run that, and then Redshift be able to consume that in from S3. And so by having this longer history, you can ensure better insight. And Airbnb said that they used the EMR to run some Hive interactive queries, and they found almost 20 to 40 times better performance by having those similar queries being stored in Redshift. So you may use EMR in tandem with Redshift, depends on your use case. But if you're doing a lot of analytical processing, Redshift is definitely going to give you better performance. So there's here's a series of resources. Again, if you have more detailed questions, we'll have a little Q&A here, but you can email me, and we can also get in touch with the database team, the Redshift team. And so you can get started by looking at Redshift at Amazon.com, aws.amazon.com/Redshift. You can also look at our marketplace. We also have documentation and a user guide and a getting started guide, so you can walk through some steps of launching a cluster and getting started. And then we also have best practices when you want to start loading, designing tables and loading large data sets. And so, we started with that brief overview. In summary, Amazon Redshift enables you to have this petabyte scale, pay-as-you-go, no upfront cost, fast performance, easy to use, point-and-click or API calls to have large clustered database solutions. And so I'd like to end this off. Oh, there's also a link at the bottom, aws.amazon.com/resources/database-services/webinars to be able to see these recorded webinars on our different services. So I'm going to connect to a cluster really quick. I'm using a tool called SQL. Oh, I'm sorry. Let me share my desktop. Sorry. So I've got I got a Workbench tool, and so when you go to Redshift, and let me go back to it really quick, you're getting a JDBC URL, and you're connecting to it as username and password, and you've got your ports, and so you've got this endpoint to be able to connect to. And so I'm configuring this. This is a SQL client. I've already got one configured using the Postgres driver. The URL, I got a username and password. I'm going to hit OK to connect. First step you would do is to create a table, right? And then you can copy the table. So I'm not going to stay long on the SQL commands, but I have a create table SQL statement. And then what we have here is a copy table name. So the way it would work is you copy the table name from your S3 or DynamoDB endpoint. You set what your credentials are, your access key and secret key, and then say what the delimiter is. So if it was a comma-separated value file, you'd have a comma as the delimiter. And so you would load that. And once you load it, you can see we have a database explorer. I've got a table here that has that table that I created. I've also got some notional data that I pulled from Census, and I'll hit So I've got population by race, by state and county in the United States from the 2010 census. And so this gives me a sample of 25 of the records. There's over 3,000 in this particular data set that you're able to do. And so once you have that in, you can verify that you've got it. And then you can run a couple queries. I'll just hit play here to run this one. And if it's 3,000 records or a billion records, I did a demo in New York and San Francisco summits where we did it over 340 million records and then 1.6 billion records. So the same concept applies. Here I'm running a query of population by state, and then I'll run one here by county. And so it's already compiled and put this through. So every time I'm executing this, you're seeing sub 10 milliseconds response times on certain of these queries. And so let's go back, before I end it, and we'll do a couple questions. I want to go back to the cluster here. And so I'll hit refresh, and it's still creating that demo one. And if I look at the example cluster, I've increased it from 1 node to 2 nodes. So that gives, hopefully that gives you a little bit of an idea of Amazon Redshift and how to operate it, what it's for, and its benefits. And so what I'll do is I'll stop this and then leave it on the last slide here, and we'll answer some questions. So let's see here. So do people use Redshift operational data as an operational data store? So most workloads there, you can use a relational database or an RDS, but it depends on, for online transactional processing type systems, or what you're calling operational to what I'm assuming, you really want to use a normal database for that. The data warehouse is more for analytics and for reporting and interactive queries to be able to go through that. Okay? And so, that's another great question is from Jim. What happens if a leader node goes down? So that's a great question. And so what happens is we actually launch another leader node in parallel. We would suspend reads and writes and access to the cluster, but another leader node will come up and take its place, and then do a DNS switch over into that leader node and resume. If the leader node fails, you're not going to lose the entire cluster. Okay, we'll take it. I think we've got time for like another question or two. Okay, let me just take a quick look, see if we can. Is it possible to collect, or is it possible to export collected performance metrics for further analysis? Yes, you can do that. You can see it in the console, but there's also system tables within Redshift that you can also do queries and be able to collect that. And then if you need it to be able to keep that offline, you can then just create a table to hold all that performance metrics. And then also there's some integrations with CloudWatch, which you can then pull as well. And is it possible to transition from a large cluster to a 8 extra large cluster automatically? In terms of automatically, because everything is programmatic, it's not a built-in service into Redshift to auto-scale this cluster size. That would still be up to you to be able to do it. You can automate it with some code in EC2 and using your command line tools or APIs to be able to increase the size of the cluster. You may have different performance metrics, like even though my total size is 32 terabytes, but because I want to massively have a parallel architecture, I'll actually have more nodes. Even though the total storage of my new cluster is a lot more capable, and I'm not storing that same amount of data, you may do it for performance reasons, where you can then stripe across multiple slices on compute nodes. And I think we have time for one more question. Let me see if I can take a look. can I move the entire database to Redshift in order to work with it and then turn down the SQL Server? You can move an entire database into Redshift and work with it and not use SQL Server, but again, that's going down the lines of your use case. If you're using SQL Server as your warehouse of data, then yes, you could export that data into flat files, into tables. You would put them into S3, format them, make sure that you're getting all the fields. In our documentation, we say what all the Postgres fields that we support and the data types that we support. And so as long as you format that correctly and you put it as files, and what you would want to do, especially with an entire database, if it's large, you want to chunk those data files so that depending on your cluster size, you can parallel import all of those files in. So there's a transformation step that you would have to do, is export that database into flat files, store them into S3, and then with S3 do a parallel copy using the copy command. And then once that's all done, you can test it, run sample queries that you would do in SQL Server. You could do that against your Redshift cluster to make sure everything's good, and then you could turn down SQL Server if you wanted to. That's if you're using it as the analytical use case. If you're still doing transactional processing like financial records, Redshift is not the solution for that. You would still want to use SQL Server. And so what we'll do is we'll answer the rest of the questions post-webinar. I really appreciate your time, and thank you for the great questions. And we'll respond back to the people who ask questions in a follow-up. All right. And that concludes it for me. Aurora, back to you.
And with that, I'll just do a final thank you. I'd like to thank you, Ben, for the great presentation today, and thanks, everyone, for attending. Bye-bye.